Hello, grades of. Welcome to the grades of mathematics summer lessons, and this is our last session on sequence and series, and this is session 7. And today we're gonna be closely looking to practical applications of sequence and series. Okay. Let's take a look at the content outline. As you can see, this is your outline for term 1 under patterns, sequences, and series. And this was the first topic. So far, we had our 6 sessions, and this is session 7. And we just swapped our session 7 and say we just gonna lastly focus on the practical applications of sequence and series. So the textbook we are still using Platinum Mathematics Learner's Book, and that's the textbook we have been using so far. Like I said, today it's our last session, and it means that we are concluding with this topic of patterns, sequence, and series. Okay, great. Unit 7, practical applications of sequences and series. And here in this unit, we're going to be solving real world problems. And I call this hashtag making learning meaningful, understandable, and relevant in or to real life. Okay, so now that we have learned sequences and series, we need to be able to know how to apply this knowledge in real world, right? So far in the 6 sessions that we've been having, you were just learning the content knowledge, how to calculate the sum, how to calculate the terms, how to evaluate sigma notation and all that, right? But you need also to be able to know how to apply the content knowledge that you have gained so far in the 6 sessions in real world, and this we're gonna do in this session, right? So in this session we'll mainly focus on some exam type real life application problems. So in the exam, they like to give you these real world problems, sort of like word problems under sequences and series, just to test whether you are able to relate the content knowledge that you have learned in real world, whether you are able to practically apply it in calculations and solving. So and thus we want to show you how you can practically apply the knowledge of sequences and series in real world. Very important. And B, most problems here are examinable, as I've said already, that examiners like using these real world problems just to test whether you are able to practically apply what you have learned. So important questions that built this session. The first one was, how can we practically apply sequence and series in our real life, right? It's a very important question. All along I've been learning how to calculate, right? I've been learning how to solve, how to calculate sigma notation, how to express series, how to prove formulas, how to derive them, how to calculate terms, how to calculate general terms, how to calculate number of terms, all those things in the 6th session. But we need to also be able to know how we can practically apply that knowledge in our real life. Very important question. How can we do that? Okay. Number 2, if we can't apply the content knowledge in our daily life, right? So if we can't apply the content knowledge in our daily life, why should we bother to learn it? Another very important question that this session will actually try to answer as we move and try to solve those different examples. If we can't apply the content knowledge, why should we bother? Why should we even bother to learn it, right? Because is it useful enough if we can't apply it? No, you see. So that's why we are saying hashtag making learning meaningful, understandable, and relevant to real life. Number 3, How can anyone be interested in learning something they cannot use in their life? Very, very important question. And that's what built this session 7. I call it one of the most important session that we have been having, or that we are having in our channel right currently. So how can anyone be interested in learning something that they cannot use in their life? One of the question, right? Can content knowledge be the foundation in which our reasoning builds? And this question, you'll see that as we move through this session, you'll be able to apply apply this knowledge, and I mean, be able to answer all these questions that really are very, very important in concluding, and in helping you to sort of like transition into the reasoning of and application of sequence and series. Okay, so in order to answer some of those questions, we're just gonna focus on the first real world example, and this is our first real world example, and I want to show you something that indeed really sequences and series can be applied in real world. So this is a question that is highly likely to be exam, or it's examinable, highly examinable question, because it's sort of like you'll see it's sort of like relate the content knowledge with some practical real world applications. Okay, so the question goes like, I mean, the statement says a specific tree grows 1.5 meter in the first year, right? So it grows 1.5 meter in year 1. Okay, so its growth each year thereafter is 2/3 of its growth in the previous year. So now they are telling you that the growth, each growth, its growth each year thereafter, in the following year, it will be 2/3 of its growth in the previous year. Okay, what is the greatest height it can reach? Very challenging question, and you can see this is a real world problem, because for example, if maybe when you reach university, maybe you want to specialize in studying our natural environment, about trees and all that, you might be really interested in learning the maximum height specific trees can reach. Thus can help also with engineering students who are also doing construction and all that, building. It's sort of like it guides them on how they can build certain buildings, and how the tree, that trees are very useful when it comes to wind. They protect certain buildings like that. So we might be really interested in knowing the maximum height the tree will reach, as thus to inform us how we can build and all that. So you can see this is really a real world problem. So they want to know the greatest height in which the tree can reach, right? But we are given something, its growth each year thereafter is 2/3 of its growth in the previous year. So when solving real world problems, you must identify which sequence is forming, right? Which sequence is forming. Is it arithmetic? Is it geometric? Is it quadratic? Or is it the combination of two, right? So let's see. In year 1, the tree was 1.5 meter. That is its growth, right? So it grows 1.5 meter in the first year. So this is the first year. So in the following years, that is second year, they said its growth is 2/3 of its growth in the previous year. So it's 1.5 multiplied by what? By 2/3, right? So if we want 2/3 of its growth in the previous year, so it's just 1.5 times 2/3, which will give me 1. So this is 1 meter. So you can see that in the second year the tree grew. Do I say grow or grew? English and maths, they don't really combine. So any pronunciation, grow, grew. So so you can see in the second year it's 1 meter, right? So it grew or grow with 1 meter in the second year. So but its total height, remember this is just its growth, right? This is the growth, but it's not its total height, right? So its total height in the second year is 1.5 meter of the first year plus its growth, which is 1 meter. So in the second year we can see it's gonna be 2.5 meter, the total height of the tree, right? In the second year. Let me just write this, the total height of the tree in the second year. When we move to third year, they said its growth each year thereafter is 2/3 of its growth in the previous year. So the growth in the previous year was 1 meter, so it's 1 meter times 2/3, right? So this would just be 2/3 meter. So this is its growth, right? But if we want its total height, we are going to the previous height, which was 2.5 meter. Then we add its growth. Then we'll be able to determine its total height. So just want you to see something. So it's 2.5 plus 2/3. Okay, so this will give me 19/6. Let me just write it like this: 19/6 meter. So it's its total height in the third year, and this will continue thereafter. You can see that this is a geometric sequence, right? Very important to identify. This is a geometric sequence. Why are we saying this is a geometric sequence? Because the next term is being determined by multiplying the previous term with a common ratio. There's a common ratio that is being used because they are telling us its height thereafter is 2/3 of its growth in the previous year. So you can see we're just multiplying with a common ratio, which we can see is what is 2/3. We can see that, right? Okay, so we want its greatest height that it can reach, right? What is its greatest height that the tree can reach? So you can see I have my 1.5 meter as the first year's height, then followed by 2.5 meter as the second year's height, then followed by 19/6 meter as the third year's height. And this will continue thereafter. It means that this will continue to what? To infinity. To infinity. Because they're just saying its growth each year thereafter is 2/3 of its growth in the previous year. So it's just going like that. We don't know when it's gonna stop, right? So to calculate its greatest height that it can reach, we need to get the sum, right? The sum of what? Of 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 its height. But this is not really the sequence, right? Because as you have seen there, if we just say 1.5 meter plus 2.5 meter plus 19/6 meter, you're just getting like this is the total height in the second year. This is the total height in the third year. It's not really gonna be accurate because uh, you are getting those total heights there. So what we can ultimately do is we're gonna create a sequence according to what we can see there. So we have 1.5 there as its first height, plus as we are going to the third year, second year it was 1.5 times 2/3, right? Remember this was its initial height, initial height, right? So 1.5 times 2/3 like that. Its growth again 1.5 times 2/3 another times 2/3. So we can say this is 1.5 times 2/3 squared, right? It's going like that, it's growing like that. It's 1.5 times 2/3 exponent 3 like that. This is going to infinity. So we need to determine the the sum to infinity there in order to get the total height or the greatest height in which it can reach, right? So my sum to infinity will be a over 1 minus r. What is our a? Remember the sequence is inside the bracket here. Let me use a different color. The sequence is here inside the bracket on the growth, right? So this was just the initial height. It was 1.5 meter, but its growth on the growth, it's where the sequence is forming, because they say the growth each year thereafter is 2 over 3 the growth of the in the previous year. So that's where your sequence starts. So your a, you can see it's 1.5 times 2 over 3, which we saw it was equals to what? It was equals to 1. Let me just delete this. Okay, so it was equal to 1. So that one was 1, and this one was what? This one was 2 over 3 meter, then like that. So our a is 1 over 1 minus, what is our r? Our r, we can see our common ratio, which is 2 over 3, right? So we can calculate the sum of its growth thereafter. So to infinity, it's 1 over 1 minus, open brackets, 2 over 3. So this will give me 3. So it's exactly 3 meters. So what is the greatest height in which the tree can reach? Its initial height was what? Was 1.5. So the greatest height it can reach is 1.5 meter as its initial height plus its total height, the sum to infinity, its growth. It means the maximum height in which this tree can reach is 3 meter. So it means its growth is 3 meter. Then we'll get the greatest height in which it can reach. So it's gonna be 4.5 meter. This is the greatest height it can reach. So it's quite complex, but it's very simple. Just need to identify the sequence, then you calculate the sum of those things going further. Okay. Okay, great stuff. Let's look at this other different example, quite similar to the previous one, but this one is much more detailed and I hope you'll understand. Okay, so it says at the end of the first year after planting, a tree is 1 meter tall, right? At the end of the first year, a tree is 1 meter tall. In the second year, its height increases by 0.56 meter. Right. So in the second year, its height increased by what? Its height increased by 0.56 meter. So it's going to be 1.56. That is its height in the second year. In each successive year, its height increases by 7 over 8 of the previous year's increase in height. So this is where our sequence is forming, right? In each successive year, right? In each successive year, its height will increase by 7 over 8 of the previous year's increase in height, right? So we need to know the previous year's increase in height. Let me just indicate it properly. This is the increase in height, which was 0.56 meter. So in the successive year, in the following years like that consecutively, its height is gonna increase by 7 over 8 of the previous year's increase. So it means that in the third year, its height is gonna increase by 0.56, which is the previous year's increase multiplied by 7 over 8. Fourth year, we can also see it's gonna be 0.56 multiplied by 7 over 8, which is the previous year's increase, then multiply again by 7 over 8. So you can see starting to form a sequence there. Okay, so the first question says, determine the increase in the height of the tree in the third year. The increase in the height of the tree. So the increase in the height of the tree, I think we have already determined. So that's the increase. It's going to be 0.56 multiplied by 7 over 8, right? So because they told us that in each successive year the height increased by 7/8 of the previous year's increase. So the previous year's increase was 0.56. We just had to multiply by 7/8. So in most real world application or problems, you'll find that the sequence is forming geometric mostly. It just forms geometric and all that. So you get that trend the more you practice. So when we multiply, it's gonna be 0.49 meter. That will be the increase in the height of the tree in the third year. So it means that in the third year the tree is gonna increase by 0.49. Okay. Okay, number 2, determine the total height of the tree after 3 years. You see, these two questions are very different, and most of the learners tend to make mistake when it comes here, right? So you need to be very careful and understand the language. So here they're saying determine the total height of the tree, not the increase. The total height of the tree after 3 years, right? It means after 3 years, how high will the tree be, like that, right? The total height of the tree after what? After 3 years. So it's very simple. So in the first year it was 1 meter, right? Then in the second year we were told it increased by what? By 0.56, right? So in the third year it increased by 0.56 times 7/8, which was 0.49 meter. That was the increase, right? So the total height of the tree after 3 years. So basically what we can do here, we can just write the increase in height from the second year. Increase in height, right? So 1 meter was the height of the tree. Then as we move, we're starting to have a sequence of the increase in what? Increase in height. Here is just the increase in height, increase in height or growth, like that. So we can see that the total height of the tree after 3 years, it will be the initial 1 meter plus the increase in height in the second year, which is 0.56 meter, about this, plus the increase in height in the third year, which is 0.49 meter. So we'll get the total height of the tree after 3 years. So it's 1 plus 0.56 plus 0.49. Okay, so this will give us 2.05 meter. So the total height of the tree after 3 years will just be 2.05 meter. Okay. Okay, let's move to number 3. Lovelo says that by the end of the 5th year, the tree will exceed the height of 3 meters. By the end of the 5th year, the tree will exceed the height of 3 meters. Tabo disagrees with him and says that the tree will only exceed a height of 3 meters after 6 years. Is either of them correct? Fully justify your answer by means of calculations. Okay, so someone is saying after 5 years, the total height of the tree will be more than 3 meter. Will be more than 3 meter. Someone says no. It is after 6 years that the tree's height will be greater than 3 meter. Let's see if either of them were correct or not. So what do we have to calculate? We need to calculate the total height of the tree after 5 years, and we just need to calculate for one of them, right? Once we get for one of them, we can be able to predict, to say okay, was correct, was not. Okay, I'm just gonna calculate the total height of the tree after 5 years, right? So after 5 years, total height of the tree after 5 years. So the total height will be our initial 1 meter plus the growth. So in the second year it grew by 0.56. In the third year it grew by, you can see it's 0.56 times 7 over 8, which we calculated to be 0.49. In the fourth year, it grew by 0.56 times 7 over 8 squared. So this we can write it as 7 over 8 squared. 7 over 8 squared. Then in the fifth year, it's going to be 0.56 into 7 over 8 exponent 3. So 7 over 8 squared, it's giving me 0.43 plus the growth in the fifth year, which is 0.38. So let's just add all those and see what we get. 1 plus 0.56 plus 0.49 49 plus 0.43 plus 0.38. So this will give me 2.86. So this is the total height of the tree after 5 years, right? So we just calculated after 5 years, but there's another one that says no, the tree will only exceed a height of 3 meters after 6 years. So let's also determine after 6 years. Let's was after 5 years. So after 6 years, the height of the tree, total height of the tree, will be the height of the tree in what? After 5 years. After 5 years, right? This is the height of the tree in 5 years, plus the growth. We need to know the growth of the tree in the 6th year, right? So the growth of the tree will be 0.56 into 7 over 8 exponent 4, because from 5 it was exponent 3, then for 6 year it will be exponent 4 there. So let's add those 2.86 plus 0.56 into 7 over 8 exponent 4. Okay, so I'm getting 3.19 meter. So who was correct? So this I think it was Tabo who said the tree will only exceed a height of 3 meters after 6 years, and it's correct because after 6 years the tree will be at a height of 3.19 meter. So it has already exceeded 3 meters. So who was correct? We can say Tabo was correct, and this is the calculation that justify, that is like the total height of the tree after 6 years. Okay, let's do number 4, which is our last question on this example. It says calculate the maximum height to which the tree will grow, right? Calculate the maximum height to which the tree will grow. So if you check the growth of the tree, we can't say that the tree is gonna die on which year. We can't really know, right? It means that its growth will just be to infinity, as no one can predict when the tree will die, right? Maybe scientists can, but okay, no one, let's just say no one can predict when the tree can die. So because no one can predict, we're just gonna get the sum to infinity. Then sum to infinity will just basically give us that total height to which the tree will grow, right? So sum to infinity is equals to a over 1 minus r, where our a, you can see, so our a is not 1, right? So don't make that mistake. 1 was just the initial height of the tree. Initial height of the tree. But what is really forming the sequence is the growth of the tree. The growth of the tree. That we can see it start on the 2nd year. So this is where your sequence is forming. Your geometric sequence is forming. From the 2nd year, this is the growth. It grew to 0.56 meter. Then on the following one, we were told it will grow by 7 over 8 of the growth of the previous year, like that. That's why we say 0.56 times 7 over 8. So your sequence is being formed on the growth, right? So to determine the total height, we are going to get the sum to infinity of the growth, then we add also with the initial height, just to determine the total height of the tree, right? So it's gonna be our A 0.56 over 1 minus our R. You can see the common ratio is what? Is 7 over 8. So after negative, just put everything in brackets. So 0.56 over 1 minus into 7 over 8. 7 over 8. And this will give me 4.48. 4.48 meter. But this is not the maximum height to which the tree will grow. Remember, the tree had an initial height of what? Of 1 meter. So the maximum height, we must also include that initial height of 1 meter plus its growth. This is its growth, like the total growth, right? So it's 4.48 meter. So this will be 5.58 meter. So this is the maximum height to which the tree will grow. Okay, so you can see when we move to practical application, that knowledge that you have been learning previously, sum to infinity, geometric sequence like that, it now has to apply. And these are the kind of questions that you get in your exam, right? Okay. Okay, our last example on this session 7. Let's look at it. It says Zukile. Is it Zukile or Zukere or what? Zukile. Okay. Zukile trained for the comrades. Okay. In the first week of training, he ran 5 kilometers per day. Be very carefully. The first week of training, so it's week 1, right? Week 1, he ran what? 5 kilometers per day. In the second week of training, week 2, he ran 7 kilometers per day. 7 kilometers per day. In the third week of training, week 3, he ran what? 9 kilometers per day. 9 kilometers per day. He ran on every day except Sundays when he rested. So you can see that in week 1 or in all these weeks, you are running every day. So they're trying to show you how many days now were there in each week. So they say he rested only on Sundays, right? It means Monday to Saturday, it's how many days? It's 6 days. So all these weeks, they have a total of 6 days in them. 6 days, right? So not the normal 7 day that we know for a week. They are telling you he ran each day except Sunday. It means in week 1 we can now get how what the total distance in which he ran, right? So it's simply to multiply that 5 kilometers he was running every day by 6 days. Then we'll know in week 1 he ran these days. These total kilometers like that. In week 2 he ran these total kilometers. So it's quite simple in that sense. So 1.1, in which week did his total distance exceed 100 kilometers for the first time? In which week did his total distance exceed 100 kilometers for the first time? This is a real world application problem, and you need to first determine the sequence. Very, very important when solving real world problems in sequences and series. You need to identify the sequence. Get the sequence first. Know whether it's arithmetic or geometric. Very, very important. Okay, so in order for us to determine this total distance, or the week in which his distance is gonna exceed 100 kilometers, we need to know the sequence first, right? So in week 1, what is the total distance that he ran? So in week 1 it was 5 times what? Times 6, because it's 6 days, you see. So let's go to week 2. Week 2 it was 7 times 6, because he ran 6 days and he was running 7 kilometers. So in week 3 it will be 9 times what? Times 6, like that. But let's get the sequence first to see. 5 times 6 is 30. Then 7 times 6 is gonna be what? 42. That's the total distance he was running every per week there. 9 times 6 is gonna be 54. So you can see this is our sequence. This is our sequence. We need to identify which sequence is this. Is it arithmetic or geometric? But I think it's arithmetic because it seems as if there's a common difference. Let's get the difference. 42 minus 30 is gonna be 12. And if you say 54 minus 42, it's also 12. So this is an arithmetic sequence. So after determining the sequence, you can now attack the question, right? So 1.1, they want what? In which week did his total distance exceed 100 kilometer for the first time? So in which week did his total distance exceed 100 kilometer for the first time? So they need what? They need n, right? They need n. Why are we saying they need n? Because we can see week 1 it's like n equals to 1. He ran 30 kilometer. Week 2 it's like n equals to 2, like that. Week 3 is like n equals to 3. So now they need n when tn is equals to what? Is equals to 100. So we can see that tn will be a plus n minus 1 d. Our tn must be 100. We want to know in which week n, where n is standing for week there. So in which week will his total distance would have exceeded 100, right? So our a is 30, which is the first term, n minus 1, our common difference is 12. Okay, let's go and solve for n. Just gonna put it there. So it's gonna be 100 minus 30, which is gonna give me 70. 12n minus 12. 70 plus 12 is gonna be 82. 12n divided by 12 divided by 12, and it's gonna be 82 divided by 12, which is gonna give me 6,83. Very tricky, quite tricky like this. So if 6,83, it means on the 6th week his total distance was like 100 or maybe 99 point something. But in which week did his total distance exceed 100 kilometer for the first time? Oh, definitely it's gonna be the following week, because on the 6,833 week it's exactly equals to 100. But for it to exceed, it means it was on the following week. That's why I'm saying it was quite tricky there. So you can convert your n equals to 7. So it is on the 7th week that his total distance would have exceeded 100, because when it's equal to 100 it was on the 6,83 what week. So it was some weeks and some days there. So on the 7th week, that's when it's gonna exceed 100 kilometers. So you must be very, very careful when solving real world application problems, because they are quite tricky, most of them. Okay, 1.2. How far did he run in the 10th week? How far did he run in the 10th week? How far did he run in the 10th week? So they need the total distance that he ran in the 10th week. So we can say they actually need term number 10, and we know it's the same as a plus 9d. So our a is 30 plus 9, our difference was 12. Very simple. So we can get 30 plus 9 into 12, then we'll get the total distance that he ran in the 10th week. It is 138 kilometers, right? So he ran 138 kilometers in the 10th week. Okay, 1.3. Determine the total distance Zukire ran during the first 10 weeks of his training. Determine the total distance Zukile ran during the first 10 weeks of his training. What do they need? They need the sum of the first 10 terms, because our terms are representing the total distance that he was running every week, right? So, but now they need what? The total distance that he ran during the first 10 weeks. So they need the sum of the first 10 terms. So that's it. Sn, because this is arithmetic sequence, Sn is n over 2 a plus last term, right? So sum of 10 terms, because they said determine the sum of or the total distance run during the first 10 weeks. What is our a? Our a is 30. What is our last term? Our last term is on T10, right? And we just calculated in 1.2 T10 the total distance that he ran in the 10th week was 138 kilometer, like that. Then just gonna get the answer. Let's see. Sorry about this. Okay, the answer is gonna be 840 kilometer. So you can see that the total distance that he ran during the first 10 weeks of his training was 840 kilometer, right? So you can see they don't actually only use geometric in real world problem. They can also use arithmetic, as we learned. So this is it was quite tricky, but you can see it's very, very simple if you first formulate the sequence. So every time if you are solving a real world problem, start with by formulating your sequence. Know what sequence is that, then you'll be able to solve all those problems. Okay. Okay, great stuff. As you know, as always, here's your fun activity, and let's see who can get this. Okay, I was supposed to write, let's see who can solve this. Okay, but that's fine. It says a rubber ball forms from a height of 1 meter above the ground. It bounces back to a height of 9 over 10 of a meter. It falls back and returns to a height of 9 over 10 of the immediate previous height. If this action were to continue indefinitely, theoretical, right? Just indefinitely to infinity in that sense. Show that the total distance covered by the ball could never exceed 19 meters. So just try this and try to solve it. Drop your answers on the comment section. I'll respond from there. If you're on the right track, give you some hints if you really want them, so that you can be able to solve it. Fun activity. Let's see who can solve this. Okay, great stuff. This marks the end of our sessions. This was the last session under sequence and series, and I hope you really learned throughout all these sessions. I'll just notify you of the upcoming other sessions for other chapters. As for sequence and series, that's how we conclude. My advice to you is go and practice past papers. Go and be solving those patterns. Go and be solving them. If you have any question, just comment on the on the comment section, then I'll just quickly respond. Or even if you have my WhatsApp number or you need my WhatsApp number, just comment on the comment section, then I'll just give you, so that I can assist you to really conceptualize and to totalize, right? So that's our aim, so that you can totalize in this topic for sequences and series. Thank you very much for being with me throughout the session. It was very, very nice having you, and thank you very much for watching, being patient, and for commenting as you always do, liking our videos, encouraging us to create more quality content videos. Okay, that's all for me, and goodbye.